Welcome back. In this video, we are going to learn Kolmogorov-Smirnov goodness of fit test, KS test in short. What kind of goodness of fit it tests? Suppose we have a population. Now, we do not know the distribution of the data. Now, this is our question. Which distribution the data is following? It may follow a normal or binomial or Poisson. We do not know that. In this situation, we may assume some distribution. Like, see these test cases. Suppose the population is errors in linear regression. Generally, we assume that the errors are following normal distribution in case of linear regression. But how far our assumption is correct? For that, KS test will help you to find out whether our assumption is correct or not. Take the second case, fairness of a coin. We know that in case of tossing a coin, we have two possible outcomes, head and tail. And if the coin is fair, then the probability of head and tail will both be equal to 0.5, right? So this is our assumption. So these kinds of assumptions we can have regarding a distribution. But before proceeding further, we must perform this KS test that will help us to find out whether our assumption was correct or not. KS test measures the goodness of fit of an observed data to a theoretical distribution. That means theoretical distribution is your assumed distribution, and you have this observed data in hand, and you find out the distribution of this data, and you try to match your distribution with the assumed distribution to find out whether the assumption is correct or not. So there is a population, and you have on this side our observed distribution, and on the other side we have our theoretical distribution. Now we try to find out the difference between this observed distribution and the theoretical distribution. If the difference is large, then we may say that our assumption is incorrect, and if this difference is too small, that means these two distributions are very close to each other, then we may say that our assumption was correct. We denote this observed distribution with f of x, and this is the unknown continuous population distribution function. Now, since this is a population and we do not have the population, then we go for samples. So, S of x is a statistical image of this f of x, and to determine this S of x, we go for computing the probabilities like this. Probability of sample observation less than x. That means if the value of x is 0, 1, 2, and 3, and we want to go for probability of sample observation SO less than equal to 2, then this will be equivalent to probability of 0 plus probability of 1 plus probability of 2, like that. So if you go for 3, then you have to add all the probabilities from 0 to 3. Like that, we have to go for calculating S of x. That means for all x, we have to find out the S of x. Clear? So the probability will be like this. Sample observation count less than equal to x divided by the total observation count. Now come on this side. The theoretical distribution is f suffix 0 of x. We denote the f suffix 0 of x like that. And this is the cumulative distribution function based on assumed distribution. That means you have the definition of your theoretical distribution. So based on the definition of this assumed distribution, you find out the probabilities. So the probability of sample observations less than equal to x, the same probability we are going to find out on this side also, but this time the probabilities will be calculated based on the defined function of the assumed distribution. Clear? So this side we are finding out the probabilities based on the data, and this side we are finding out the probabilities based on the definition of the distribution, of the assumed distribution. And if we want to say that our assumption is correct, then S of x and f0 of x must be close to each other. Clear? Okay. Now you see how it works. we have to go for this d suffix n, and this d suffix n is actually the maximum absolute deviation between s of x and f0 of x. And we have to find out the maximum deviation among all the absolute deviations for all the x's. That means if your x starts from 0 and goes up to 3, then you have to find out the difference between s of 0 and f suffix 0 of 0. You have to go for s of 1 minus f0 of 1, like that, up to s of 3 and f0 suffix 3. F suffix 0 of 3. So in this way, you have to find out all the deviations for different values of x's, and you identify the maximum deviation among all these deviations, right? Now, why maximum absolute deviation we are looking for? Say, we have to look for the worst case scenario. If our null hypothesis is true, then for all xi, s of xi minus f suffix 0 of xi will be less than critical value, right? That means all the deviations, whatever you have calculated over here, must be below some critical value. Now, if you want to be sure that all the deviations are below critical level, so you go for only one value, which is having the maximum value. So if we can establish maximum of these deviations is less than critical value, then it is obvious that the other deviations which are lesser than this maximum value will also be less than critical value, right? That is why we are finding out which is the maximum among these, and we compare that maximum with the critical value, and we can take the decision, right? Okay. So what are the steps? First, you define null hypothesis, because your KS test is actually testing your null hypothesis. Next, you determine s of x, and that calculation will be based on the observed data what you have in hand. Next, you determine the f suffix 0 of x, which will be based on the definition of the assumed distribution. Next, you find the deviations between s of x and f0 of x for all the values of x. Okay, you take the absolute deviation. Next, you identify the point or points. Actually, you may have this maximum deviation in more than one places, right? It doesn't matter whether it appears in one place or more than one place, okay? And your step 6 will be obtain the critical value of test statistic at the given alpha, that is your level of significance, under the condition that the null hypothesis h suffix 0 is true. So you consult the critical table with this alpha value and find out the critical value over there. And next you compare that critical value, that is d suffix n comma alpha. So this is your critical value and this is your computed value. And if you find that your computed value is greater than equal to the critical value, then you reject the null hypothesis. That means your assumption regarding the distribution is wrong. Otherwise, you do not reject the null hypothesis. That means your assumption regarding the distribution was correct. Let's take an example. Suppose we talk to 400 viewers with 100 samples for their opinion on a movie in the form of like and dislike. Now we want to test whether the opinions were fair or not. That means whether the viewers were biased or not. So we go for testing the fairness of opinions at 5% level of significance. Now this is the data we have, and our assumption is it is following binomial distribution. Why? Because the data has two outcomes, like and dislike. And also there's a possibility that the opinions were fair. So like and dislike both are important here, and thus each goes with 0.5 probability, right? Now you see that the possible like count in a sample 0, 1, 2, 3 and 4. So for this, actually the table is having this like count as 0, 1, 2, 3 and 4. Now the question is, why the table carries 0, 1, 2, 3 and 4? See, we have the sample size as 4. That means 400 are the total viewers over there. So that is also a sample actually. We are making this 100 samples as 100 sets, you can say. We are dividing the samples into 400 viewers, that sample of 400 viewers into 100 small sub-samples, you can say. And in each sub-sample, we are having 4 viewers over there. Now, all of the 4 viewers can go for dislike. In that case, you will get 0 over here. That means all the 4 has given dislike. That means 4D. In the second column, you see that 1. That means 1 person has given like and 3 other persons have given dislike. In this case, 2 given likes and 2 given dislikes. Here 3 gave likes and 1 gave dislike, and here all of them gave dislikes. Likes. This is the reason we have all these columns, right? Now for 0, that means all of them have given dislikes. The frequency is 23. 1 like was there for 95 times. That means 95 viewers gave 1 likes. 164 viewers gave 2 likes, like that. And you add this figure and you will get 400. Now we go for the null hypothesis. Our null hypothesis says that our assumption regarding the distribution is true. That means f of x is equal to f suffix 0 of x. That is, the distribution function of our data is equal to the assumed distribution. And mind this condition, for all x, that means you have to have for each x this equality. Now if one of the x's fails to maintain this equality, that means f of x is not equal to f0 of x for at least one x, then it becomes alternate hypothesis. f0 of x is a cumulative distribution function, that is CDF, of our assumed binomial distribution, and we have the value of n as 4 because each sample size is 4, and we have the probability of likes as 0.5. S of x we know already, that is a total sample observation count from the lowest value of x up to the present value of x, for which you are looking for this S of x, divided by the total observation count. So here we go for S of 0 because x starts from 0 from here. This one is x, this side up to 4, and it starts from 0. So we first go with x equal to 0. So S of 0 is 23 by 400 because 23 viewers over there who went with dislikes. So we got this 0.058. Next we go for S of 1. For this, you have to count the frequency for 0 as well as 1. So 23 plus 95, and it gives 0.295. Next you go for S of 2. For S of 2, you have to count this 23, 95 as well as 164, and you will get 0.705. For S of 3, you count from 23 up to 92. And for S of 4, you count from 23 up to 26. And this is actually equal to 400. So the S of 4 becomes 1. So we have got the S values for all the x's, right? Now we go for calculation of the f0s for all x's. We have this f0 of x equal to probability of observation count less than equal to x. Now what is the probability of observation count equal to x? So it goes like this. It is familiar to you that NCx p raised to x 1 minus p raised to n minus x. So we know that this is the definition of the function of binomial distribution. So we go for the value of x equal to 0. So f0 of 0 will be probability of observation count equal to 0, and this gives you 4C0 because n's value is 4. Here this will be 4 and the x will be 0 at this moment. So 4C0, 0.5 raised to 0 because in binomial distribution, the value of p is 0.5, and the value of 1 minus p is also 0.5. So 0.5 raised to 0, and here 0.5 raised to 4 minus 0, that is n minus x, and this gives 0.0625. We go for f0 of 1 now, and we have to go up to f0 of 4. I'll show you one more, and the rest of the f0s you can calculate by your own, right? So f0 of 1, this is the probability of observation count less than equal to 1. That means you have the probability of 0 as well as the probability of 1 added together. Now we have this first term as 0.0625. So we have to go for this observation count equal to 1. So probability of observation count equal to 1 will be like this. 4C1, the value of x changes, the n's value remains same, and 0.5 raised to 1, 0.5 raised to 4 minus 1, and this gives us 0.25. So the f0 of 1 gives 0.0625. This is the first term, and this one is the second term over here, and we get 0.3125. In this way, you can go for f0 of 2, and you will find this, f0 of 3, this one, and f0 for 4 as this one. So we have got all the values for s as well as for f0s. Now here is the table. This column is for tail count. This is observed frequency. This is the cumulative observed frequency. And this one is the observed distribution frequency, that is s of x. And this is the theoretical distribution frequency f0 of x. We are interested in these two columns at this moment. And the last column is the deviation, absolute deviation between s of x and f0 of x. That means this column and this column. So you take the absolute deviation between this one, and this will give you this deviation. This is the absolute deviation between these two. So for these two, you have the deviation over here. In this way, you have all the deviations, and you notice that we have the maximum deviation as 0.0175, and it appears in two rows, in two places. It doesn't matter. We are only interested in the maximum deviation, not in the number of places it is appearing. So we write here dn is 0.0175. So this is our maximum deviation among all those deviations. Now we go for the KS test table, and this chart is actually giving you up to 40 from n equal to 1 to 20 and from 21 to 40. And our sample size, total sample size is 400. So it is not in this chart. And for that, they have given us to follow one approximation whenever you have a sample size greater than 40. So here is our assumption. Here is our approximation, 1.36 by root over n. And this approximation is aligned to 0.05 for a two-tailed test. Now, why we have chosen this one? That's two-tailed test. You remember our alternate hypothesis, f of x is not equal to f0 of x. So it may be less than or it may be greater than. In this example is a two-tailed test. So we take this row, two-tailed test row, and our level of significance given is 0.05, and we got this one. So the critical value will be like this, 1.36 root over n. That now do not be confused with this n and the n we have used before. So this n is actually the meaning of the whole sample size, that is 400. So 1.36 root over 400 will give you this. We have got the d suffix n over here. If the computed dn is greater than equal to the dn comma alpha, that is the critical value, then we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. Now, our computed dn is less than the critical value. So we do not reject the null hypothesis. That means we can say that the opinions are fair. So our assumption is correct that the data follows binomial distribution. I hope it's clear to you how to use KS test to determine whether your assumed distribution is correct or not. If you have any question, then you can write me in the comment box. That's all for now.